Hi there, I'm Jawad Mustafa and I will be presenting our work titled Guiding in-Context Learning of Large Language Model through Quality Estimation for Machine Translation. It's joint work with my PhD supervisors, Dimitar Shterniov and Peter Sprank at Tilburg University. Generative large language models quickly gain popularity and continue to do so because of their performance on a large set of natural language processing tasks, including machine translation. However, the accuracy of their inputs is highly influenced by the quality of the in-context examples provided to them. If these examples are not appropriately selected, meaning if they do not align well with the specific task and source domain, the LLM's output can be inaccurate. So it's super important to develop better methods for selecting appropriate examples that actually match the task and source domain being translated. Traditionally, creating in-context examples for machine translation involves either random selection or using a strategy such as maximizing an evaluation metric like BLUE to choose examples that improve the metric. Random selection is simple and easy in terms of implementation, but it can lead to inconsistent results and end up being costly in terms of computation. However, recent state-of-the-art in-context learning approaches focus on retrieving training examples that are closely relevant to the context of source sentences using unsupervised retrievers such as BM25. Plus, recent research shows that things like the order of examples, the templates used, the domain, and the number of examples you pick can all significantly affect the translation performance. Naturally, the most effective in-context examples for a given source text are the ones that would impact the resulting translation quality, which would ultimately depend on translation references or human judgment. In machine translation, we know that a quality estimation has become the standard approach for evaluating an empty system's output without relying on reference translations. Also, recent studies showed the effectiveness of domain-specific quality estimation in contrast to the ineffectiveness of generic QE when it comes to domain-specific machine translation. Building on this, and to address the aforementioned challenges, our work proposes using domain-specific QE to help select the best in-context examples for machine translation. The goal is to find the optimal number of in-context examples and their combinations to enhance machine translation quality, all without needing reference translations. By evaluating the impact of different in-context example combinations and sequences, we hypothesized QE could not only improve translation performance, but also reduce processing time. This is mainly because QE might lead to smaller sets of in-context examples, which would cut down on inference times. This is especially important given the limited number of in-context examples that can be fed into large language models. So our study aims to explore how effective domain-specific QE models are in selecting in-context examples for translation tasks in large language models. To utilize LLMs for effective machine translation, what is needed is a set of examples to provide the context, and as a result, guide or steer the LLM toward the correct context-specific translation, meaning a set of in-context examples. And what is further important is the number of in-context examples and their combination. Ultimately, what is required is that the in-context examples provide context that is neither too specific nor too broad and can effectively boost the translation. Our goal with this work is to develop a methodology that optimizes both of these aspects in order to deliver high-quality machine translation. Our methodology for identifying effective in-context examples involves two key components. One, an unsupervised retriever that finds examples closely related to the sentence to be translated, and two, a search algorithm that uses QE to select a combination of examples that leads to the improvement of translation quality. In other words, aiming to maximize the BLUE score. In this slide, we outline an example of how our proposed methodology works. We use the BM25 ranking algorithm because it's proven effective for unsupervised retrieval. BM25 ranks training pairs source text and their translation based on how relevant they are to the sentence we want to translate. We then pick the top K sentence pairs from the BM25 ranking. Here, K is the parameter that controls how many pairs we use in our search. We follow three main phases in our search algorithm. Phase number one is selection. We choose the highest ranked training example from the initial set of K examples provided by BM25. This example is added to our list of selected examples. Obviously, in the first iteration, there are no previously selected examples. In phase number two, translation, the selected example is translated by the model. In phase three, estimation, we use a domain-specific quality estimation model to evaluate the quality of the translation by comparing it to the original source text. After estimating the translation quality, the selected example, its quality score, and the translation output are added to an intermediate list. The list is sorted by estimated quality in descending order to keep track of the best result. Obviously, to avoid duplication, the selected example is removed from the pool before the next iteration. This process continues until the translation quality stops improving according to a set of patience threshold or until all the K examples have been selected. In summary, our methodology iteratively refines the selection of in-context example to ensure the highest quality translations based on both the QE model and the LLM's output. Our methodology enables the systematic selection of in-context examples that enhance translation quality compared to previous in-context learning methods, while efficiently managing the computational resources needed for the search process. We achieve this efficiency by incorporating early stopping conditions with the predetermined patience threshold, which helps avoid unnecessary computations. It is important to highlight that we don't explore all possible permutations of the initial in-context examples, as this would involve numerous attempts and significantly increase computational costs during the search process. We conducted 4 main experiments to test how effective our methodology is. 3 of these experiments compare our approach to existing in-context learning methods in different setups or modes. The 4th experiment compares our method to a fine-tuned pre-trained language model, namely Embark 50, to see which one gives better translation. Mode 1. In Mode 1, we use QE with in-context examples ordered by BM25. This was to test how well combining BM25 and QE works in our in-context learning methodology. In Mode 2, here we explore the impact of ordering in-context examples by n-gram overlap, more specifically unigrams, along with QE. Since previous research has shown that ordering in-context examples by their n-gram overlap with the source text can be effective, we wanted to see how this affects translation quality. We reorder in-context examples based on their n-gram overlap, calculated using the NLTK board tokenizer, so that in-context examples with higher overlaps were fed into the large language models earlier. Mode 3. In Mode 3, instead of using QE, this mode involves computing the BLEU scores on the existing test set. While this isn't obviously a realistic scenario, it represents the best case scenario, serving as a high benchmark to compare against Mode 1. The search algorithm of our proposed methodology generates up to 16 candidates. For each mode, we ran experiment using 3 different early stopping patience value, 3, 8, and 16, to determine the maximum number of in-context examples generated. We included patience 16, which means no early stopping, to see how the model performs when using the maximum number of in-context examples. Also, the search process stops if the estimated quality score hits or exceeds 100, which prevents any further evaluations. Our proposed methodology requires a sentence-level QE model to effectively guide the selection process of the search algorithm. Given the success of domain-specific QE models in previous research, we developed our own domain-specific QE model to enhance the selection process. This development involves two key phases. In phase one, we trained a QE model using out-of-domain data to ensure generalizability. We used the German-English Europath dataset from Opus to develop our generic QE model. However, as empty datasets like Europath typically consist of pair of source and translated text, it was necessary to synthetically create post-editing text. To do so, we used MBART 50 to translate 1 million randomly chosen source text from Europath. Next, the resulting translations were considered as machine translation text, with the corresponding reference translation acting as post-edited text. In phase two, we fine-tuned the model using the training set to provide domain-specific QE model and address domain mismatch, which is a critical issue in both machine translation and quality estimation. In our experiment, we used blue as the quality label or quality goal label because our study focused on translation performance rather than post-editing effort, which is typically evaluated using HDR. For the architecture, we used the mono-transquest architecture from Transquest framework. In our experiment, we used the XGLM model because of its strong performance in machine translation and to ensure a fair comparison with previous research. Specifically, we used the 7.5 billion parameter version of XGLM and its tokenizer from Hugging Face. We worked with a dataset of German to English translation first in the IT domain. This choice was made to address difficulties machine translation system and LLMs face with out-of-domain context. The dataset included about 222,000 training sentences, 2,000 development sentences, and 2,000 test sentences. To evaluate the translation effectiveness of the models, we employed metrics such as BLEU and COMET. We compared methods from previous study, including random sampling, task level sampling, BM25, RBM25, and a fine-tuned MBART 50 model. Details on how we implemented these models are available in our paper. As shown in Table 1, RBM25 with 16 examples outperform the other methods and is the best performing approach in the literature, which is why we chose it as our baseline. We found that increasing the number of examples improved the score across all methods, though this improvement comes at the cost of increased prediction time. This pattern was consistent for both the COMET and the BLEU metrics across all methods. Specifically, our approach in Mode 1 improved the BLEU score by at least 0.52 points with the patient's threshold of 3 and by up to 1.58 points with a patient's threshold of 16 compared to RBM25 with 16 examples. The result from Mode 2 indicate that all three patients' thresholds outperform the methods in the literature, though the improvement is not statistically significant compared to Mode 1. This suggests that ordering examples by n-gram similarity does not boost translation performance in our approach. In experiment 4, we found that while MBART 50 is designed for translation across 50 languages, it did not exceed the performance of the RBM25 method with 16 examples, which was the best among existing methods. It only outperformed random sampling, task level sampling, BM25, and RBM25 with just one example. Although fine-tuning MBART 50 improved contextual performance according to COMET, the process was significantly more time-consuming than identifying in-context examples and generating inferences with XGLM. We know that from prior studies that pre-trained large language models often over-generate, leading to extensive post-processing. Figure 1 compares output lengths for our model, specifically Mode 1, patients 8, and RBM25 using 16 examples. As we can see, Both align well with the reference, indicating no overgeneration. However, RBM25 differs significantly, while our model closely matches the reference, suggesting it requires less post-editing and is more efficient. On the right side of this slide, you see an example of selected in-context examples for a source text. We also analyze the number of in-context examples and CO2 emissions for different approaches. However, due to the time constraint, these details are skipped here, but are available in our paper. To sum up, we have developed a new in-context learning method that boosts LLM translation and makes better use of computational resources. By using domain-specific query, we have fine-tuned how we select in-context examples, moving behind the old approach of just relying on development set references. Our method involves finding relevant examples with BM25 and picking the best in-context example combination using a query-guided search. Our tests on German to English IT datasets show that our method beats previous ones in BLEU and COMIT scores, though it does use more computation. Ordering in-context examples by unigram overlap didn't make much difference. Compared to fine-tuning NBART 50, our approach gives better translation and lower carbon emissions. For future work, we would like to test our method with different languages and domains, try out other metrics, and look into additional features like bigram, type token ratio, and length for selecting in-context example. We also plan to work on reducing the computational load to make it even more efficient. The code of our experiment is available in the GitHub repository, so we can reproduce our results. That's it. Thank you for your attention. I'm happy to answer any questions.